Good morning, everyone, and welcome to today's live webinar. My name is Mshedi V, and together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today's presentation will be given by my colleague, Mr. Murtaza Bohra. Murtaza is the R&D manager of the academic applications team at Quanser, which develops teaching content and research examples for our systems. In the last 6 years, Murtaza has been involved in developing flight controllers for the Q drone, research quadrilateral, autonomous applications for Quanser's self-driving vehicle, the QCar, as well as undergraduate teaching content for the QArm robot manipulator. He's also represented Quanser globally in workshops, trade shows, planetary talks, and conferences. Murtaza holds a master's in applied science in space mechatronics and a bachelor's in engineering science from the University of Toronto, where he has taught a graduate course on manipulator robotics as well.
Hello, everyone, and welcome to today's webinar. I'm Murtaza, and I'll be introducing you to Quanser's Python APIs and content examples. I want to start this session with this video showcasing prominent languages from 1965 to 2020. Python enters the scene around 2001 and quickly climbs to become the most popular programming language by the end of 2019. Why is Python so popular? Not only is it easy to use and has hundreds of libraries and frameworks available for development, it's also adopted by big corporations such as Facebook, Google, and Amazon, increasing both demand for engineers and programmers that are comfortable with it, as well as available support in the community. On a slightly different yet related note, here is a chart that showcases Quanser's product line over the last 30 years. We have worked with academics and met their demands for research and teaching equipment over the years, but what particularly interests me is the software that we provide to go along with that. We have focused on making an academic's life easier when it comes to software by letting them focus on their research, which involves performance, but also simplifying the interface to hardware while keeping the flexibility to customize it. I'd like to bring your attention to WinCon 1.0 in 1993, which allowed you to use controller structures with pre-canned diagrams to use with our hardware and tune them. Eventually, WinCon 2 added MATLAB and Simulink support. In 2008, Quanser's real-time control software, Quark, was released, which streamlined WinCon's functionality and improved user experience. It is very recently, in 2020, that we added support for most of our robotic and control systems devices in Python, starting with the QCar, right about the same time as Python became the most popular programming language. About a year ago, I held a training session where I drew this map to summarize what Quark, a rapid control prototyping software for MATLAB and Simulink, included. This representation is very crude and minimalistic. Quark includes a lot more features that are not captured here. But again, I want to draw your attention to one of the items in here, everything inside the box marked with the number 2, referencing our APIs. The hardware and the loop API to access hardware I/O, the stream API for communications, the multimedia API to access cameras, and more. These APIs are embedded within our Simulink block set, but are also available in Python and C. Before we look at code and examples today, let's start with documentation. Start by visiting our website in your favorite browser while not judging me for using Microsoft Edge. Go to Quanser.com and look up Quark in the search menu at the top right. Once the page loads, scroll down to find our documentation link. Once you get there, expand User Guide at the left and get to External Interfaces to find the Python documentation. You could have also found the C documentation right there. There are 5 APIs here, and we'll be looking at 3 of them today: hardware, multimedia, and communications. Here's an example of the read function documentation under the hardware category. Not only does it give you information on the parameters and built-in error handling, but it also gives you sample code to show you how it all comes together. I cannot go through example code without, of course, making sure that we cover installation. So let's go ahead and do that. Launch your favorite web browser again and visit python.org. Download the latest 64-bit version. And remember, when you launch this, to add Python to your path automatically. It only takes a couple of minutes to get most of Python installed, but before you close the installer, make sure you disable the path limit near the end. Launch a command prompt to check that everything's good. Type in Python, and it should not open the Microsoft Web Store. It should instead give you a Python terminal. You can check that it's the version you've installed, and it's 64-bit. First thing to do is always check your version of pip, which is the package manager. Even though this was a fresh install, you'll need to upgrade it. Next, we'll install some common packages we'll need: NumPy, OpenCV, Matplotlib, and SciPy. With an internet connection, these packages will automatically download, as well as all their dependencies. Then it'll install them. For the final installation step, browse to the directory where you downloaded the wheels for the Quanser Python APIs. We will still use pip to install them, but this time we'll find the links for these wheels in the local directory. If you install Quanser API, it will install all of them. As a sanity check, generate the list of packages so far using pip again. This will confirm that you have everything you need. Let's go over how all these modules, the 5 of them that we just installed, come together. The 5 APIs that we just installed form the low-level libraries. These were developed by Quanser's software team. These give you full customization options with our devices. Next up, we have the mid-level libraries that Quanser's application team develops. These don't necessarily add features, but rather use the Quanser Python APIs at the low level to create classes and methods that represent the most common configurations and use cases for our devices. Educators might find these useful as starting templates, while researchers might most likely ignore these. Higher up, you have your code, or my examples today, that make calls to these mid-level libraries. These examples are designed to be student-facing, simplifying their lab experience to a few lines of high-level code. All of these may also make calls to other standard packages like NumPy or OpenCV. Lastly, your code can also directly make calls to the low-level APIs. Researchers and advanced users might find the flexibility very useful. Let's explore the module structure through some examples. We're going to take a look at 3 examples in total. The first one is a classic PD control example with the QUBE Servo 2 device. To access the hardware, we will use the Hardware in the Loop API. Here is a mid-level library for the QUBE Servo 2. Before I expand these, let's take a look at this at a high level. At the very top, we have a definition for a QUBE Servo 2 class object with 5 methods. The init method serves as the constructor when you create an instance of this class, and then we have 3 methods that simplify the I/O: write voltage, write LED, and read position and speed. The terminate function gracefully closes the connection to the device. Notice the little red rectangle at the bottom right of your screen. On any slide that shows code, this box will tell you if it is a mid-level library developed for support or a high-level example for students. The mid-level libraries don't do anything when you run them, but the high-level examples are focused on some particular task. I will not be opening or directly going through the low-level libraries as they are fully documented, and I've shown you where the documentation lives. I will, however, highlight any calls made to the low-level APIs. The init function starts with an instance of the HIL class, which is the low-level API call, taking the QUBE Servo 2 USB tag and the device ID as parameters at line 33. At line 40, we write a high value to the digital channel 40 so as to enable writing to the motor. At line 37, we also reset the encoder counts back to 0. Lastly, if the user creates an instance of the QUBE Servo 2 class in task mode, it creates a task reader at the specified frequency to use an independent hardware clock for timing. If you specify a normal mode, the QUBE uses immediate I/O, but you will have to handle timing for the application yourself. Next, we have the write voltage and write LED methods that use the low-level write method. The read position and speed method reads in either immediate mode or task mode, where the latter uses an independent hardware clock. And the terminate method writes a 0 voltage value at the end, sets the LEDs back to red, disables writing to the motor, and closes the reading task gracefully. Now comes the high-level student example. This creates an instance of the QUBE Servo 2 class that we just took a look at. Within the main while loop, it first reads the position and speed data at line 25. A square wave command is generated at line 28. A PD controller, proportional derivative, is used at line 31. And the voltage command it generates is written to the QUBE Servo 2 at line 35. If any error is caught or the simulation time elapses, the QUBE instance is gracefully shut down at line 49. Now let's go ahead and run this code. After a brief delay, the code starts and the LEDs on the QUBE Servo turn green. You can see the QUBE following the 45-degree amplitude square wave for 2 periods. In the end, some plots will be generated that will show me both the position response as well as the voltage response. Next, we will interface to the QArm manipulator. The QArm has 4 degrees of freedom and a gripper, and the HIL API can be used to move these joints. In addition, the QArm also includes a RealSense camera at the end effector, and we can use the Media API to access the camera feed as well. Much like the QUBE Servo 2 class, the Camera 3D class defines various methods to simplify use case. The init method lets you pick and start RGB or depth streams in various resolutions and frame rates. The terminate method shuts down the RGB and depth streams correctly before terminating the RealSense camera instance. The read RGB method reads a frame from the RGB camera, puts that in its buffer, and returns a timestamp for that data as well. The read depth method reads a frame from the depth sensor, but you can choose whether you want it in unsigned in 16 or directly in meters. And then you have some additional methods that let you define intrinsic and extrinsic matrices if you've given additional parameters for the camera, such as focal length. This is the high-level student-facing example that reads and shows the camera data. After creating an instance of the Camera 3D class that we just took a look at, for reading both the RGB and depth, the while loop reads the frames in lines 28 and 29, and then uses OpenCV to display the images from lines 31 to 33. If a keyboard interrupts the code, Control-C, or the simulation time elapses, the camera connection and instance is terminated gracefully. For completeness, I'll also show you the code that I'll be running in the background to move the QArm manipulator using the HIL API. Much like the QUBE Servo 2 class, here we have a QArm class. It creates an instance of the QArm right at the top, and then some analytical utilities such as inverse kinematics available in the QArm utilities class. I generate a position command, pass it to inverse kinematics on line 39, and then write the joint positions to the manipulator at line 43. The QArm code's running in the background. Let's run the RGB-D imaging camera example. And as the arm moves, we can see the images being displayed by OpenCV. Lastly, let's take a look at the QBot 3. This will include multiple examples. The first, or 2 applications actually. The first one will use a couple of QUBE Servo 2 devices to generate the steering and throttle commands. These will be interpreted as forward and angular velocities for the QBot, The second application will be running on the QBot. It will receive these commands and drive the QBot. In addition to using the HIL API in both these applications to access the three devices, I will also use the Stream API to pass information between the two applications. The basic Stream class is just another one in the mid-level libraries to simplify server-client communication using Quanser's Stream API. The init method lets you define the instance of basic Stream, both as a server or a client, using the agent flag right there. Then you have a method to check incoming connections and poll. You have a terminate method to correctly shut down connections as well as the streams. You have a receive method that automatically adjusts to different types of data and sizes and receives data in chunks if needed. And then you have a send method that does the same thing in reverse. This is the student-facing example that is going to be deployed on the QBot 3 itself and will be running on a Raspberry Pi 4. The code initializes a stream instance as a server, as well as a QBot 3 instance for I/O. In the main loop, we check to see if the server has found an incoming client connection, and if so, we accept it and alert the user, and then enter the third if case. In here, the server receives two values from the client, which it then interprets as the forward velocity or the angular velocity, while adjusting for convention and applying a gain. And then I pass those velocities to inverse kinematics, which turns them into left and right wheel velocities. I send that back to the client just for monitoring. And then I write that to the QBot's I/O, the left and right wheel velocity commands. This is the second application, again, front and student facing, which will be working with the QUBE servos. It initializes two cubes as well as a basic stream instance as a client in this case. You can see the IP address of the QBot right there, which is where the server is located. After checking the connection near the top, in a very similar way as to we did with the server, we enter the third stage when connected, and I go ahead and read the position and speed data from both my QUBE Servo 2 devices. I then pass them to PD controllers, which have very low gains. I want some reactionary feedback from my two servos, and if I ever let them go, I want them to come back to 0. And then I send the two measured positions to my QBot server. And that's mainly it for this application. In the end, I terminate everything gracefully. So let's go ahead and run this code. At the top left, I'm browsing to the local directory on my laptop that has the code for the two QUBE servos, which is application 2. And then at the bottom left, I have a command prompt where I'm going to try and ping the QBot 3 to see if it's connected. It gives me a response, and I can move ahead and SSH into it. Now that I'm in, I'm going to browse to the application directory on the QBot 3 where I transferred the files. I used WinSCP to transfer them, but you could also use a USB drive if you wanted to. The example we want is drive QBot, so we're going to prepare that one. We will run the server application first, followed by the client, which is the QUBE application. The LEDs on the two QUBE servos at the bottom right have turned green. You can go ahead and try and rotate the QBot, and you can see it responding. And I use the other QUBE servo to give it velocity commands. To terminate this, I terminate the QBot 3 server application first, and you'll notice the client automatically detects that and terminates as well. Now, what about virtual hardware? Quanser Interactive Labs includes identical digital twins for our hardware and virtual representations. Can Python be used there? This QUBE Servo PD control example that I ran earlier with the hardware cube, we can use the same example with Quanser Interactive Labs. If you modify the ID parameter from 0 to include a reference to the virtual cube's network location, which is my local computer, the example will run on the virtual cube. In most of our examples, you will instead find a keyword argument called hardware. You can set it to 0 to represent virtual solutions instead. The constructor method for the device classes, the QUBE Servo or QArm, automatically append the appropriate virtual plant addresses to the ID tag when you do this. This is the QArm example that we just ran earlier, now deployed to the virtual QArm. You can also deploy the code for RGB-D imaging that gave you the camera feeds to this virtual manipulator as well, which I have not done in this case. To end this webinar, I'd like to mention some future developments that we are working on. Look forward to upcoming content in Quanser Interactive Labs for the self-driving car studio, which includes a full-scale driving map with the ability to spawn crosswalks, traffic lights, road signs, dynamic pedestrians, and multiple queue cars, and set up self-driving applications, all from Python. Also check out our Quanser GitHub page. We'll be adding quite a few examples there in the upcoming months to help you get started. We'll also be adding the Python application libraries repository with a variety of mid-level libraries for our popular devices, in addition to other examples like April tag detection or camera calibration. The self-driving car studio repository will also be added with focused examples on exploring an autonomous driving stack. That brings us to the end of the webinar. Thank you for joining me today. If you have any questions, I'll be happy to answer them.
Thank you very much, Murtaza. That was a great presentation. We've had a number of questions from the audience. So the first one is from Professor Chang is asking if the Python API can be used with a Quanser shake-table system.
That is a very good question. I myself am not aware at the moment, but I can have one of us reach out to you. Most likely it should be possible. A lot of our devices that you can access from MATLAB Simulink using the HIL initialize block also have support added in Python. So most likely it is possible, but we can double check.
Does the Python API support the Q8 USB?
Yes, it definitely does.
Okay, so that is probably a possibility.
Yep, then we should be good.
Okay, we have another one here. Can I implement the Python code on the QBot 2E system?
Yes, you can. The QBot 2E has the Raspberry Pi 3B Plus installed on it. And as far as I know, it already has Python 3 installed on it. If you want the wheels for Python packages, please reach out to us since the Python support was added later, but we can help you get that set up as well.
Okay. And we have one question from Shane asking if it's possible to run a Quark Python script simultaneously with a Simulink Quark model on the same device and pass data between them. If so, is it best to pass data between using the stream block functions?
It definitely is. So both the stream functions in Simulink, which are the, let's say, basic stream server client, as well as the stream functionality in our communications API in Python, they are essentially the same, but they are wrapped differently. And so you can set up a server in, let's say, MATLAB Simulink and a client in Python and have them interface or pass data to each other. You can also use models concurrently or simultaneously. That depends on what data you're actually accessing. So let's say you have an accelerometer on a sensor on one of our devices, and it's currently being read in Simulink application that's deployed, or Quark application deployed on the system. Then you are not going to be able to simultaneously access that in Python, but you can have different applications accessing different sensors if you want.
Great, thank you. One question again, one more question from Mr. Akaya. How do we get installed workspaces and interactive labs?
If you are interested in Quanser Interactive Labs, I would point you to our website where you can ask for more information on this, and we'll get you in touch with our regional partner manager, and they will work with you to get you either a trial or see if you're interested in it. You can find more information about it on our website as well.
Perfect. Last question, Murtaza, is how do you achieve the proper timing in these examples in Python?
Timing's a little sensitive, but you have two classical ways of doing it. The first one would be where you just use immediate I/O, which means you're accessing our HIL API to get one sample of data, and that's about it. And then you run through the rest of your code, and you manage timing yourself, which mainly involves something like the time module, and you do a time.sleep, and you try and sleep for as long as you want to. And when you wake up, you come back to the top of the loop, you get data again and repeat. Of course, this is not the most optimal way of doing it. The other option would be to use task-based I/O, which uses an independent hardware clock for timing. In this case, the read operation is actually blocking with an independent hardware clock that only gives you data at the specified rate. In this case, you can run the rest of your code as fast as you want. And every time the loop comes back to the task-based read, it will automatically hold until the specified sample time has elapsed, which gives you the real-time performance you need. The examples that I ran today, the QArm example was using the time.sleep method, whereas all the other examples were using task-based I/O. In the QBot 3 example, I had the QBot 3 using task-based I/O, as well as blocking stream communications. And then the QUBE Servo examples were using immediate I/O as they were getting their timing from the QBot 3.
Great. Well, thank you very much once again, and thank you everybody for joining today's webinar. For additional information on how to use our products and services to enhance your engineering labs, please visit our website at quanser.com and on LinkedIn. And on that note, have a great day, everybody.